Welcome back to the course on audio signal processing for music applications. In this demonstration class, I want to talk about periodic signals. Periodic signals are at the basis of understanding most signals and are also at the basis of Fourier analysis. So it's good to talk a little bit about them. Let's start by opening Audacity and generating some periodic signals. So here it has a tone generator, and the most fundamental periodic signal is the sine wave that we already have seen. So let's generate a sine wave of 500 Hertz, duration of 5 seconds, and amplitude 0.8. Okay, so here is our sine wave. Let's hear it. Okay. In order to see that it's periodic, we can zoom into it, and here we see the sinusoidal oscillation, the periodic oscillation of a sine wave. If we zoom even more, we're going to start seeing the samples that are present in this signal. This is a discrete signal, so we have generated this signal at 44,100 Hertz, so we'll have that many samples per second. Okay, so the first thing we might want to do to understand the concept of periodicity is to measure what is the period length. The idea of periodic means that there is a period that is repeating a cycle of the sound. Okay, so this is a cycle of this sinusoid, and in here we can see what is the length of this selection I made, and it says that is 0.002, so that means 2 milliseconds. If we go to the terminal and have Python in, we can use it as a calculator, so we can convert this period length into frequency. So the inverse of the period, so 1 over 0.002, will be our frequency. And of course, it gives us 500 Hertz. 500 Hertz is the frequency of this sinusoid. Okay, another thing we might want to check is, okay, this period has a series of samples. So how many samples does one period of this sinusoid has? Well, in order to compute that, what we should do is start with the sampling rate. The sampling rate is 44,100, and multiply it by the duration of this period. So we multiply it by 0.002, and it gives me 88.2, which is the number of samples of a period. Of course, it should be an integer number, so I guess it's going to be 88 samples in one period. Okay, now let's generate another sinusoid, but of a different frequency. So let's maybe open a new file. Okay, and let's create another sinusoid, but instead of 500 Hertz, let's put, for example, 5,000 Hertz. Okay, so this is the sinusoid of 5,000 Hertz. We can hear it too. Okay, clearly much higher, and we can also zoom and to see the periodicity. But here we already see that is not so nice. In fact, the samples are not really shaping a smooth sinusoidal function. This is because there is less samples per period, therefore we don't have a very smooth version. So how many samples are in one period? Well, not that many. In fact, here we can even count them, and it's 1, 2, 3, 4, 5, 6, 7, 8. So in fact we have like 8, 9 samples per one period. Not exactly, because they don't coincide, of course, with a period. Of course, it makes sense, because if we had seen that the frequency of 500 had 88 samples in one period, now that we have 10 times the frequency, 5,000, the number of samples will be 10 times less. So it's going to be around 8 or 9 samples. That's pretty good. Of course, this relationship between the number of samples and the frequency is a very important one and related with the sampling rate. The bigger the sampling rate, of course, more samples we'll have, and for higher frequencies we'll have more samples. At 44,100, as we go up in frequency, and if we go even higher, like 10,000 or even 15,000, the number of samples will be very less, and therefore the shapes will not look like a sinusoid, even though it's a sinusoid. Okay, let's look at another periodic signal, but different from a sinusoid. So we will create a new file, and we will generate a tone, but in this case let's generate, for example, a sawtooth. And instead of 5,000, let's go back to the 500 Hertz. And maybe the amplitude, we don't have to put it that high, because this is a very rich sound and it will be quite loud otherwise. Okay, so this is a sawtooth waveform. Again, we can now listen to it. Okay, if we zoom in into this waveform, well, we see that it's very periodic, and since the sampling rate is high enough and the frequency is kind of low, we can, if we zoom in, well, we have a lot of samples per period. But in this case, the period, which we can measure, and it's going to be the same thing, 500, it doesn't mean that there is one frequency at 500 Hertz. In fact, this waveform has many frequencies. It has 500 Hertz as the fundamental frequency, and it has multiples of that, so that it's a harmonic sound. And how can we check that? Well, we check that with a spectrum analysis. And in the Audacity, we have the possibility to plot the spectrum. Okay, and here now it tells me that there is not enough data because I have to choose a bigger part of the sound. So let's choose a bigger fragment of the sound. And now if we replot, now we can visualize the spectrum of this sawtooth. And clearly we see that it's a quite complex spectrum in which it has many peaks. In order to understand this, I think it's good to compare it with the sinusoid we started with. So this was the sine wave we started, and if we do the same thing that we have done now with the sawtooth, that is to compute the spectrum, well, we see now that it's clearly very different. The spectrum of a sinusoid has only one major peak at the frequency, in this case 500, and the spectrum of this sawtooth has many peaks which correspond to all the frequencies present in this harmonic signal. Okay, now let's even do something a little bit more complicated. Let's see that we can generate one signal, but instead of being the same frequency all the time, let's have it that it changes in time. So these are normally called chirp functions. So let's have a sine wave being a chirp, and let's go from the two frequencies we have mentioned. So from 500, let's go up to 5,000 Hertz, and let's have the amplitude as 0.8 all the time, and let's have these 5 seconds. So now we have kind of a glissando, a chirp, and of course we can play it again. Okay, so it's a frequency that goes up, and again we can zoom, but we will see that the period keeps changing in time. So at here at the beginning we'll have a period that is going to be quite long. It will be the 500 Hertz, the 2 milliseconds, and by the end it will be much smaller. It will be 10 times smaller. Okay, and of course we can visualize that by analyzing the spectrum of this signal. So if we select a portion at the beginning and analyze the spectrum, we will see that it has the around 500 Hertz frequency, And if we go to the n, so we go to the n of the signal here, and now we compute replot the spectrum, well, it has shifted. It's going towards the 5,000 hertz, so it's also one single peak, but much higher. Okay, and that's a good way to visualize and understand periodic signals. Okay. Anyway, so this is all what I wanted to say today about periodic signals. So let's go back to the slides. And well, we haven't used much. We basically have used Audacity, and we have talked about electronic periodic signals, synthesized periodic signals. These are signals that are quite good to play around with because we know how we generate them, and so therefore when we analyze them we know what to expect. So in next demo class we will complicate that, so we will actually analyze more complex signals, sounds, that might have some part of the periodic, might have some parts that are not periodic, so they reflect more the reality of real sounds. So I hope to see you next class. Thank you very much.